All right, today we are going to go over all of the different types of inhibitors. So we're going to go over competitive inhibitors, non-competitive, mixed non-competitive, and uncompetitive inhibitors. So we're going to go through how each of these inhibitors affect Km, Vmax, what a graph would look like, what a Lineweaver-Burk plot would look like, and then what just a velocity over substrate concentration graph would look like. So this is the goal of what we're going to get to. Let's get started. I'm going to start off here by just what a normal graph would look like with no inhibitors. So we can define all of our values. So Km is going to be the dissociation constant. Vmax is going to be the max velocity. All right, and we're going to make two graphs for each of these inhibitors to kind of visualize what they do. So the first one is going to be the substrate concentration over the velocity. Without an inhibitor, it is going to look something like this. And so we can say this here is going to be Vmax. It's important to know that this here is half of Vmax. And where this point crosses the x-axis is going to be the value of Km. And we can also recognize that Kcat is Vmax over the enzyme concentration times time. So this is the coefficient for catalysis. And so now we're going to draw our Lineweaver-Burk plot. And this is going to be 1 over V, and this is going to be 1 over S. And this is going to look a little something like this. Now this point here is 1 over Vmax, and this point here is 1 over Km, where it crosses the x and where it crosses the y-axis. Now an equation that we can use to visualize this is 1 over V equals Km over Vmax times 1 over S less 1 over Vmax. And if we can recognize this is just our y equals mx plus b, 1 over v is y, 1 over s is x, and then our y-intercept b is 1 over Vmax. And then Km over Vmax is going to be our slope. All right, so now that we have the baseline done of all of this, we're going to move on to our first inhibitor, which is going to be a competitive inhibitor. The important things to note for competitive inhibitors is that Vmax is the same, Km increases. So I'm going to draw an arrow. And this one binds to active site only. And it can be overcome with an increase in substrate concentration. And this will make a little bit more sense when we draw the graph. We have our substrate concentration and then we have velocity. If we remember, our uninhibited enzyme looks kind of like this. Now, if we want to raise Km without hindering Vmax, the line is gonna look kind of like this. So we can say that our Vmaxes are the same, but here our 1/2 Vmax is now at two different spots. So this was the original Km. Extend over here, this is our new Km, which we can see is a lot greater than our original Km. And this should make sense because if we have something, an inhibitor that is binding to the active site only, it is going to make it harder for the substrate to bind. And so Km, if we remember, is our dissociation constant. So all of this inhibitor that's fighting for the same active spot is going to make the Km higher. So it's going to make that dissociation constant for the substrate higher. It's going to be harder for the substrate to bind. But as we said, it can be overcome with a lot of substrate. So if we have a lot of substrate and it just overwhelms numerically wise a competitive inhibitor, it's just going to work as normal. So that's why our Vmax is the exact same, because once we get to a certain concentration of substrate, there's so much substrate compared to the inhibitor that it's just going to reach its normal Vmax, which we can see by this graph here. Now let's look at our Lineweaver-Burk plot. Our inhibited one is going to look like this, and our non-inhibited one is going to look like this. And it crosses at the x-axis because we said 1 over Vmax. Vmax is the same. So it's going to have the same y-intercept. Now here, 1 over Km, 1 over Km. This one can be tricky because they're inverses, but if we think about 1 over Km, if Km is increasing, that means the fraction is decreasing. So that's why this value here is smaller or closer to 0. So that is competitive inhibition. Next, we are going to move on to non-competitive inhibitors. So for non-competitive inhibitors, The Km is going to be the same here. And actually the Vmax is what is going to decrease. Non-competitive inhibitors bind to somewhere other than the active site. So it can either bind to the enzyme itself or the enzyme substrate complex. So that's important to note. So binds somewhere other than active site. And so this can either be the enzyme or ES. So this means that it can bind to the enzyme when it is free of the substrate or also when it has a substrate attached because it's not affecting the active site at all. So we can draw our plot. This is what our normal graph would look like. And this is what our inhibited graph would look like. This is Vmax. Now, if we try to find Km on the uninhibited graph, it's gonna be somewhere around here, because this is where half of that Vmax is. Now, if we want to find it here, it's probably going to be right here, which is the exact same spot. So the Km is the same and the Vmax is different. If we want to draw this on a Lineweaver-Burk plot, it is going to look like this. As we can see, 1 over Km is the exact same, but the Vmax's are going to be different. So because in the inhibited version Vmax is less, that means the fraction is actually going to be bigger, so it's going to be above that other one. So important to remember that inverse relationship. Okay, we finished non-competitive inhibitors, and now we are going to move on to mixed non-competitive inhibitors. For these inhibitors, Km can actually increase, or technically it could decrease. This is what's special about mixed inhibitors, is that I remember it's mixed because it could do either. It usually only increases Km because it increases that dissociation constant, making it harder for substrates to bind. But in certain cases, it can also lower that Km, so important to note. Now, Vmax is also decreased in this case. Now, the way that mixed inhibitors work, I think it's easiest to visualize this when we draw it out. First, we have enzyme plus substrate separate. Then it turns into enzyme substrate complex, which we'll say ES. So this is when the substrate has binded to the enzyme. And then this goes straight to enzyme plus product. Now, where our inhibitor fits in is if we add an inhibitor here, this can go to either EI plus S, or if we add an inhibitor here, this can go into ESI. And these can also interchange between one another. So this is basically saying that the inhibitor can bind to either the enzyme itself or the enzyme substrate complex. So this is why you often kind of get two different mechanisms for either Km increasing or Km decreasing, because it can bind to any one of those. Again, mixed inhibitor, the name kind of tips you off. So I'll go ahead and just write can bind to E or ES. All right, now let's move on to our graphs to kind of visualize this. This is going to be our uninhibited enzyme with our Vmax here. And then our inhibited enzyme is going to look a little something like this. So our Vmax is up down here now. So Vmax has decreased. If we're going to look at Km, this is about where Km is for our uninhibited enzyme. And then for our inhibited enzyme, it's going to be way over here. So Km has increased in this case. Now let's look at our Lineweaver-Burk plot. Our inhibited graph is going to look like this, and our uninhibited graph is going to look like this. This is 1 over Km. And so as we can see, the purple line, Km, increased, which means that the fraction decreased, so it's closer to 0. 1 over Vmax, 1 over Vmax. Purple line, we can see that Vmax has decreased, which means that the fraction has increased. Okay. We finished mixed inhibitors. Now our last type of inhibitor that we're going to talk about is uncompetitive inhibitors. For this one, Km is going to decrease and Vmax also going to decrease. And this is because it binds ES only. All right, now let's visualize this. So our uninhibited enzyme is going to look something like this, and our inhibited enzyme is going to look something like this. Now if we want to draw Km, it's going to be about here. Now Vmax is also about right here. So our Km is going to be about right here. So as you can see, Vmax has decreased and Km has also decreased. So what's unique about this one is that The Km decreasing means that the dissociation constant is decreasing, which means that the substrate can be held on more tightly by the enzyme and it won't be disassociated as quickly. This is something that sets this enzyme apart from the other one. This is the only one that consistently always lowers the Km. Now, mixed non-competitive inhibitors can lower the Km, but it can also raise the Km. But competitive strictly only lowers the Km, and it's easy to remember this because it only binds to the enzyme substrate complex. So it's binding to that enzyme substrate complex and it's not letting that enzyme let that substrate go. That's how it's inhibiting it. So that's why the dissociation constant is so much lower. All right, and then the last thing that we're going to do is look at this Lineweaver-Burk plot. These two lines are going to be parallel. That is a good tell for uncompetitive inhibitors. This is because 1/Vmax has decreased, which means that the fraction has gotten bigger. And then 1/Km has also decreased, which means that fraction has also gotten bigger too. All right, so this is all that we have for our inhibitors. This is a little bit of a simplified version as I didn't go into all of the nitty-gritty alpha values and stuff like that, as that's not as important. That's going to be more important for a biochemistry class than the MCAT, for example. But my original note sheets that I showed at the beginning of this video has all of that values, so that will be the one that I post on the link tree. It's the exact same thing as this, it just has some extra information like equations and stuff. That is all I have for you today. The notes will be on my link tree. This will be under biochemistry notes, and then it will be titled inhibitors. So yeah,